So in this video we're going to explain some things about open sets and continuous maps. So we're going to do this at least initially in the context of metric spaces. Right? So let x and y be metric spaces. So we've got metrics. Remember that means you've got a function that we'll call dx from x cross x to the reals, and dy, say, from y cross y to the reals. Okay, so dx measures distance between points in x, and dy measures distance between points in y. And suppose you've got f from x to y as a function. So here's the usual metric space definition of continuity. So f is continuous if for all points x and x and epsilon greater than 0, there exists delta greater than 0 such that whenever x prime is in x, with the distance in x between x and x prime less than delta, we have the distance in y between f of x and f of x prime is less than epsilon. So let's just kind of recall what this means a little bit. So and the idea is that you've got our point x in capital X, and you've got some tolerance epsilon greater than 0. We want to control f of x prime, where x prime is going to be something close to x, and so you would expect that f of x prime should be close to f of x if f is continuous. And so we need to be a little quantitative about that. So what do we mean by close? So given some epsilon greater than 0, you want fx prime to be epsilon close to fx, as measured by this dy. And in order to guarantee that, we need to x prime is going to have to be close enough to x, so that closeness is measured by this delta greater than 0. Okay, so that's the standard kind of the standard metric definition of continuity. But it turns out that we don't really want to work with that. We want to work with an alternative definition, an alternative characterization of continuity that will work in a larger context with topological spaces instead of metric spaces. So in order to describe that, we need to remember about the definition of open sets in metric spaces. So we're going to use this definition here. Let X be a metric space. A is going to be a point in X, and R is going to be some positive real number. And I'm going to use the notation OBAR. It's the open ball. Radius R around A. So this is defined to be just the set of those points x and x for which the distance from between A and X is less than R. Okay, so that's the open ball. We can also consider the closed ball, where that would be a less than or equal instead of less than, but this is the one we want for the minute. And having defined these open balls, we can define what we mean by a general open set. So I'm going to suppose we've got some metric space again and some subset of it. So we say that U is open if rule A and U exists some radius R greater than 0, such that the open ball around A, radius R, is contained within U. And maybe we'll have a quick look at this interactive thingy about this. Okay, so here are two sets, A and B. Okay, sets in the plane, and A, you can see the edge is kind of fuzzy. You're supposed to understand that means that the boundary circle is not included as part of the set A, but on the right hand side we've got the set B, which does include the boundary circle. And so we've got a typical point in A, as where the cursor is pointing. Then we can draw a disk around it that's wholly contained within the set A. And as we get closer and closer to the boundary circle, we need to make that disk smaller and smaller in order to be surrounding our point and still contained with A. But we can always do it. No matter how close we get to the edge, we can still draw a disk around that selected point that's contained wholly within A. So that's illustrating the fact that A is an open set. And it kind of works more or less the same as B, right? You've got points in B, then you can try and surround them with a disk, and you can usually do that. In most points, you can choose a disk contained wholly within B, and centered at the chosen point. But it doesn't work if we go to the edge of B, right? If we choose a point that's actually right on the boundary circle, then there's no way we can draw a disk around that that's contained within B. But whenever we draw a disk around that point, it'll always poke slightly outside B, and so we'll be stuck. And so that's the difference between between an open set and a set that's not open. Okay, so okay, so then we get our definition of closed is just the complement is open. Right? So subset F, you can look at the complementary set. It might be written as F upper C for the complement, or as X backslash F. Both just mean the complement of F. And we say that F is closed if and only if the complement is open. Okay. So notice, if you were to look in the notes on metric spaces that we're using as our standard reference for this section, you'll see that, well, our definition of open sets is exactly the same as in the metric space notes. So our definition of closed is different. But there is a theorem in the metric space notes. That's on page 43 of the metric space notes, which shows that the definition used there for closed sets is equivalent to what I've given here, so it doesn't really matter. Okay, then there's some key points, some key properties of open sets that we need to remember. Okay, so this is a proposition that's from page 44 in the metric space notes, if you're looking through those. Any metric space X, the empty set and the whole space these are kind of two trivial examples of open sets, the empty set and the whole set. And then the union of any family of open sets is open. And then the intersection of any finite family of open sets is also open. So in other words, if U1 up to UN are open, then so is U1 intersect U2 up to UN. Okay. So I think I'm not going to say anything about the proof of that here. That's proved in the metric space notes or in just about well, absolutely any book that you might look at with metric spaces. Okay, so now I want to discuss how we can characterize continuous maps just using open sets. So again, this is something that is done in the metric space course, but I'll just at least mention the result here. But for that, there's another ingredient we need, which is about preimages. So let f from x to y be a function between sets. With this definition, we don't need these to be metric spaces or anything, they're just arbitrary sets. Okay, so then we define the preimage, f inverse b, that's a set of those x for which f of x lies in b. Okay. So this is obviously a subset of x, right? So b is a subset of y, f inverse b is a subset of x. Okay, so that's now of course this notation f to the minus 1, that has kind of another meaning, and which is strictly speaking logically separate. So we should examine how these are related. So remember, if f from x to y is a bijection, if it's a bijection, there's an inverse map called f to the minus 1 from y to x. So f of f inverse y is always equal to y, f inverse f of x is always equal to x. Okay, so then what in this context, so this thing, the definition of preimage, that works perfectly well whether or not f has an inverse. But if it does have an inverse, then you can do this alternative thing. You can just look at this set B, and then you can apply f inverse to all the elements of B, and that gives you a subset of A, and it's just a tiny exercise that's exactly the same thing as the preimage. And so these two kinds of notation now are logically separate, but they tie together perfectly well in the case when they're both defined. So let's just record some basic properties of these preimages. So we've got so f inverse the empty set is the empty set, and f inverse the whole space y is just the whole space x. Secondly, Okay, so if you've got some family of subsets of Y, then you could firstly take their union and then take the pre-image of the union. So that's going to be a subset of X. Or alternatively, you could take the pre-images individually and then take the union of those, and that would also be a subset of X. But they're actually the same subset. And also, it works the same in intersections. So each BI is a subset of Y, pre-image F inverse BI is a subset of X. You take the intersection of all those subsets. Or alternatively, you first take the intersection of BIs and then you take the pre-image, and that's just going to be the same. Another thing, F inverse is also compatible with taking complements, right? So you've got your subset B of Y, then you can either firstly take the complement within Y, which would be called B complement or Y less B, and then you take the pre-image of that. Or alternatively, you could take the pre-image first and then take the complement of that, but it doesn't matter what you do, you get the same answer. And thirdly, okay, so we've got two maps that follow on from each other like this. F goes from X to Y and then G goes from Y to Z. And now suppose you've got some subset C of Z. And there's two things you could do to that. I mean, firstly, you could just sort of take the composite map, G composed of F from X to Z, and then take the pre-image of C with respect to that. Or alternatively, you could do it in two steps, right? You could take the pre-image of C under G, and then that will give you a subset of Y, and then you could take the pre-image of that subset using F, and that will give you a subset of X. But again, these things are the same. Okay. So this is again proved in the metric space notes. I'll just give you prove one of these things as a sample. So let's prove two. Okay, so okay, so I've got some element X and X, and so if I want to prove that these two sets are the same, then I need to show that X is contained in this set, if and only if X is contained in that set. But so this, for X to be an element of the pre-image of B complement, that's the same as F of X to be contained in B complement. That's just the definition of F inverse. That's equivalent to saying that F of X is not in B. Okay, so that's just the definition of B complement. That's equivalent to saying that X is not in F inverse of B. That's just the definition of F inverse again. And that's equivalent to saying that X is in the complement of F inverse B. That's again just the definition of complements. So X lies in this set, if and only if X lies in that set, and so these two sets are actually the same. And all the other parts of this lemma can be proved in a very similar way. Okay, so the key fact about these pre-images is like this. There's the proposition. there's three equivalent conditions on a map between two metric spaces. Firstly, that f is continuous. By the usual epsilon and delta definition that we wrote down a minute ago. Secondly, the pre-image, you take any open set V and Y and you take its pre-image, which is a subset of X, so that's got to be an open subset of X. And the third condition, that the pre-image of every closed set is closed. Okay, so here's three different things that are equivalent to each other. So yeah, if we know that f is continuous, then it follows that the pre-image of every open set's open, pre-image of any closed set's closed. Similarly, if we know that the pre-image of every open set is open, then it follows that the map's continuous. And so again, the proof is. I'm not going to give it here, I'm just going to remind you that this is true. It's in the notes on metric spaces, or in just about any book on metric spaces as well. And so in the next video we'll see how this leads us on to the general definition of topological spaces and continuity of maps between topological spaces.